In this video, we will demonstrate the new diagnostic validation capability introduced in eXpress 6.5. Starting from the system level design, we're able to begin by choosing any specific level of hierarchy within the design. We select this level as determined by how far down in this hierarchical model we intend to isolate. This will enable us to quickly construct a diagnostic tree of our system based on the tests defined at that level of hierarchy, along with the pre-packaged default eXpress diagnostic algorithms in this case. But this tree can represent a couple different diagnostic scenarios. If this were troubleshooting diagnostics, you could think of this as a troubleshooting procedure where we could perform a test. If it passes, we'd move down in the tree and it highlights in the diagram what's proven good. If the test fails, we would move to the right in the tree and it colors in yellow the items that are under suspicion until we perform the next test. If, on the other hand, we're dealing with a health management type paradigm, where we're getting snapshots of different sensors or fault codes at any particular time, we can think of this as a fault signature lookup table, where we have a series of failed tests or fault codes that are being produced by, for example, out-of-scope sensor readings, and we're using this as a way to take that set and determine the associated failures. It's like a checklist for being able to determine what these tests mean. So we could say that if the first, second, and third tests correspond to fault codes that were reported by bit, then the bit diagnostics would immediately isolate to this diagnostic connector. If this bit test were to fail, while this fault code did not report a fail status, but these remaining bit tests reported a failed status, then we've isolated to a fault group that contains this pump relay here and the ECU. So the type of diagnostics described and evaluated in the diagnostic tree shall depend on the various purposes of the diagnostics, as they are related to any sustainment approach or mix of implementations. But what we really want to talk about is the ability to validate our diagnostic integrity. By validation, there are several different meanings one may be referring to. One might be, did we model everything correctly, and does the diagnostics we developed make sense from an operational standpoint? Another type of validation is being able to insert several faults into the system and being able to show that they're going to be isolated correctly. However, before we do that using an actual fielded system, we can do it here and insert faults and see what the diagnostics are supposed to isolate to, based on the development we did and which tests were used. Additionally, we could perform a preliminary maintenance demo by inserting faults. In this manner, if we aren't generating the same results as expected, we can actually step through our diagnostics in our model, see what was happening, and figure out if there was a problem in the implemented diagnostics in the field. Whether there was a problem in assumptions made by the diagnostics as contained in the model that aren't being completely transferred into the field, or whether we actually have any errors in the model. So this comprehensive diagnostic validation capability was designed to help in all of those scenarios. By clicking on the Desktop Fault Insertion button, we'll get this dialog. We'll go to the Insert a Fault screen, and we can choose a fault we want to insert. This can be something that you agreed with the customer, or something that you're interested in investigating. For example, let's say a pedal linkage failure. We can then click Diagnose Fault, and that shows us the fault group that is isolated. We can discover the sequence of tests that led to that isolation. The entire fault signatures, which are all of the tests that were used for diagnostics that would have failed if this fault were to occur, whereas the diagnostic test sequence is showing that really only 2 tests failed of those 5 particular tests that were required to isolate the failure. We can observe the diagnostic inferences as we move through step by step and see which components are being proven good or called into suspicion, with each step simply by inserting any fault manually. We can also do random insertion of faults. With this mechanism, we can select any number of faults at random. In this case, it's selecting random faults using a setting that is allowing for a maximum of 2. So each time we say random, this means that we're going to get either 1 or 2 faults. And then we can just diagnose any of the faults randomly inserted, even faults that happen to not be detected. But notice that we could have seen that before clicking on that selection by seeing that the fault signature has nothing in it. Here's one that would have a lot of tests that would fail if it were to occur. This particular solenoid has several ECU fault codes that would be reported. The test sequence actually makes use of 5 of those. But what you could do is review the test sequence. First of all, does this make sense for this fault? Does it make sense that these would be the tests that it uses? You can see if there's anything over here that looks wrong. If you're just doing a sanity check, you can do a whole bunch of these randomly inserted faults and see where and how it diagnoses. Now this can also be done as a report. We can set our faults up in a spreadsheet if we wish to insert specific faults, or we can randomly insert them. This enables us the opportunity to systematically evaluate every fault one at a time and see how they're isolated. This can be stepped through regardless of the number of steps in the diagnosis. For example, we can also reverse direction and proceed one step at a time through any complex diagnostic sequence in an exhaustive manner. So one of the more common uses of this diagnostic validation tool is typically as a sanity check of the diagnostics that can be performed along with a subject matter expert, or SME, early and at any point of the development life cycle to ensure that our model has captured the diagnostic design in its entirety. This can be performed long before we're ready to field the diagnostics, allowing us to have the confidence that the model and our diagnostics accurately represent the system the way it's supposed to. So if something isolates, you can look at the tests and make sure that it's something that makes sense. Going further, typically part of a diagnostic validation process may be to randomly insert faults but allow the randomness to be weighted by failure rate. Thus, the random selection then drives the demonstration activity. For example, depicting how the bit tests are able to successfully detect and isolate some percentage of those randomly selected faults, and then how that relates to the overall system performance of the implementation of the bit. We can observe the performance of such bit capability either through interactivity with this GUI or under diagnostic validation. There's also the fault insertion report, where we can select random combinations. If we should choose to list the fault signature all failed tests, let's do 20 failure combinations. And then if we'll select fault sequence, we'll be able to quickly push this detail into a spreadsheet that describes, for this particular random failure, here's the bit test that would fail, here are the bit tests that are used in the sequence. Therefore, if true bit failure randomness is what we are striving to check, then that can be fully interrogated and exploited. Another scenario, for example, is when you're doing a maintenance demo or a fault insertion with a customer. You have worked with the customer to be able to develop a list of faults to be inserted, whether there's 20, 50, 100, etc. And then the customer can choose some or any of the faults randomly that may be performed in an actual demo. We can insert these faults into the system using this diagnostic fault insertion mechanism and see what and how it is isolated. But if we desire to retain this diagnostic validation detail for continued purposes, we can simply export all of this detail to a spreadsheet. So for example, let's randomly insert faults into the pump motor. This would be a simple method to instantly vet the same health or diagnostic bit test coverage or any other test interrogation that would occur in an actual maintenance demo. When we have captured the diagnostic implications of the faults that we want to be able to list for our presentation to our customer, we can actually export the comprehensive detail of these results to an Excel file where, over time, we can gradually append any labels that may provide additional collaborative diagnostic clarity. Then, in the future, we're able to import this detail from the spreadsheets interactively to how the diagnostics would be isolating any of those faults in the diagnostic validation report. Imagine the power of inserting any randomly generated faults into the system, regardless of complexity or hierarchy. Such a capability not only provides a mechanism to evaluate, assess, and demonstrate the diagnostic integrity of the bit at any hierarchical level of the design by itself or combined with any other diagnostic implementations, but it is fully interoperable and transferable to the diagnostic implementation of the bit to the system's evolving health or maintenance paradigm. Be sure to view other videos available from DSI's video tutorial library for further insight into the advanced use of DSI's Desktop Fault Insertion for modernizing your system's diagnostic capability effectively and affordably.